RAF Debden, England, June 16, 1944, and Captain John Peterson of the 4th Fighter Group stands beside his P-51 Mustang, watching ground crew pump a strange new fuel into his aircraft's tanks. The fuel is purple instead of the familiar green of 100/130 octane, and the technical officers have briefed him that this experimental 150 grade aviation gasoline will allow him to push his Rolls-Royce Merlin engine beyond any limits he's known before. What Peterson cannot possibly know as he climbs into his cockpit is that within 2 hours he'll intercept a German V-1 flying bomb, screaming toward London at 400 miles per hour, and only the chemical composition of the fuel in his tanks will give him the speed necessary to catch and destroy it. The transformation of Allied fighter aircraft from capable interceptors into speed demons that could dominate any enemy represents one of the most significant yet least understood technological achievements of World War II. A story of petroleum chemistry, metallurgy, and desperation that begins not in aircraft factories but in research laboratories, where scientists struggled to understand why aircraft engines destroyed themselves. The problem that would eventually lead to 150-octane fuel development had plagued aviation since the earliest days of powered flight, manifesting as a sharp, metallic knocking sound inside engines, followed by catastrophic failure. Pilots in World War I reported the phenomenon, describing how their rotary engines would suddenly lose power, emit strange sounds, and sometimes explode without warning. Engineers called it detonation or knock, but understanding what caused it and how to prevent it would require decades of research into the fundamental chemistry of combustion. The issue stems from how gasoline burns inside an engine cylinder. Under normal conditions, the spark plug ignites the fuel-air mixture and a controlled flame front spreads smoothly across the combustion chamber, pushing the piston down with steady pressure. But, under certain conditions, particularly high compression or high boost pressure from superchargers, pockets of unburned fuel-air mixture ahead of the flame front spontaneously explode before the flame reaches them, creating shock waves that slam against pistons and cylinder walls with tremendous force. These shock waves create the characteristic knocking sound and, more importantly, generate extreme local temperatures that can melt pistons, destroy bearings, and crack cylinder heads in seconds. The octane rating system emerged in the 1920s as researchers at General Motors sought a standardized way to measure fuel's resistance to detonation. They discovered that different hydrocarbon molecules had vastly different knock resistance, with iso-octane exhibiting excellent anti-knock properties, while normal heptane knocked terribly. By defining iso-octane as having an octane rating of 100 and normal heptane as 0, they created a scale against which all fuels could be measured. A fuel with an octane rating of 87 performed equivalently to a mixture of 87% iso-octane and 13% normal heptane in a standardized test engine. This rating system allowed petroleum companies to refine fuels specifically for resistance to detonation, enabling engines to run at higher compression ratios and produce more power from the same displacement. The military implications of octane rating became apparent during the late 1930s as aircraft designers pushed for higher performance. The Rolls-Royce Merlin engine powering the Supermarine Spitfire represented cutting-edge technology in 1936, but its designers understood that engine power output was fundamentally limited by the fuel's octane rating. The Merlin used a supercharger to compress intake air, allowing more fuel-air mixture into each cylinder and thus generating more power. But increasing boost pressure meant increasing the likelihood of detonation, and detonation meant destroyed engines. British engineers calculated that every 3-point increase in octane rating would allow approximately 1 pound per square inch additional boost pressure, translating to roughly 30 additional horsepower from the Merlin's 27-litre displacement. In the desperate mathematics of aerial combat, where a few miles per hour could mean life or death, these calculations mattered intensely. Royal Air Force fighters entered World War II using 87-octane fuel, the same grade available to civilian aircraft. But British petroleum chemists had already begun developing higher octane fuels, using a chemical discovered almost by accident. Tetraethyl lead, synthesized by Thomas Midgley Jr. at General Motors in 1921, proved to be an extraordinarily effective anti-knock additive when blended into gasoline at concentrations of just a few grams per gallon. The lead compound interfered with the chain reactions that caused spontaneous ignition of fuel-air mixtures, allowing fuels to achieve octane ratings far beyond what refining processes alone could produce. By adding 4 cubic centimeters of tetraethyl lead per gallon, petroleum companies could boost 87-octane base stock to 100 octane, a transformation that would prove crucial to Allied air superiority. The United States possessed enormous advantages in producing high-octane aviation fuel, controlling both the petroleum resources and the industrial capacity necessary for large-scale production. American refineries adopted catalytic cracking processes that broke heavy petroleum fractions into lighter, higher-octane components, while alkylation units recombined small molecules into larger ones with better anti-knock properties. By 1940, American refineries were producing 100-octane aviation fuel in quantities that seemed almost wasteful to European observers accustomed to severe fuel rationing. The transformation of Merlin-powered fighters using 100-octane fuel demonstrated what higher-octane fuels could achieve. Spitfires that had struggled to exceed 360 miles per hour with 87-octane fuel suddenly achieved speeds over 370 miles per hour when 100-octane became standard in 1940. The additional boost pressure allowed by the higher-octane fuel enabled Merlin engines to produce over 1,300 horsepower instead of the 1,030 horsepower they generated with 87-octane, a 26% power increase from simply changing fuel. RAF pilots during the Battle of Britain credited 100-octane fuel with giving them a crucial edge over Luftwaffe fighters still using 87-octane B4 fuel, allowing Spitfires and Hurricanes to outclimb Messerschmitt Bf-10-9s at critical altitudes. German aviation engineers understood the problem, having developed their own high-octane fuel called C3, with a 96 over 125 octane rating. But chronic shortages of the specialized chemical additives required for C3 production meant that most Luftwaffe fighters operated on 87-octane B4 fuel throughout the war. The North American P-51 Mustang emerged from an unusual requirement, designed in 1940 to British specifications by an American company that had never built a fighter aircraft. The first Mustangs used Allison V1710 engines and achieved respectable performance at low altitude, but suffered from the Allison's poor high-altitude power output due to its single-stage supercharger. The transformation that would make the Mustang legendary came in 1942, when Rolls-Royce test pilot Ronald Harker flew a Mustang 1 at Duxford and immediately recognized that installing a Merlin engine would create an exceptional aircraft. The marriage of North American's aerodynamically refined airframe with the Merlin 61's two-stage supercharger produced the P-51B, an aircraft that could escort bombers to Berlin and back while fighting German interceptors along the way. The P-51B demonstrated speeds exceeding 440 miles per hour at 30,000 feet, cruising ranges over 1,300 miles with drop tanks, and climb rates that matched or exceeded anything Germany could field. By late 1943, Allied petroleum chemists had begun exploring fuels that could exceed 100-octane rating, investigating ever more complex additive packages and refining techniques. The challenge was that octane rating, by definition, topped out at 100, corresponding to pure iso-octane. Fuels better than pure iso-octane required a new rating system, leading to the development of performance numbers, where 100/130 meant the fuel performed as well as iso-octane on the lean mixture scale, and 30% better than iso-octane on the rich mixture scale. The rich mixture rating mattered most for combat engines running at maximum power with fuel-rich mixtures to cool cylinder heads and prevent detonation. Shell Oil Company's researchers developed a fuel designated 100/150, later standardized as 44-1 fuel by the Army Air Forces, that used massive doses of tetraethyl lead combined with other additives to achieve performance 50% better than pure iso-octane under rich mixture conditions. The development of 150-grade fuel represented a triumph of industrial chemistry, requiring new refining processes and quality control measures. The base stock had to be carefully selected from specific petroleum fractions rich in branched-chain hydrocarbons that resisted detonation. Catalytic reforming converted straight-chain molecules into branched ones, while polymerization combined small molecules into larger, more stable compounds. The additive package for 150-grade fuel included not just tetraethyl lead at concentrations approaching the solubility limit, but also ethylene dibromide to prevent lead deposits from fouling spark plugs and valves. The resulting fuel was purple, coloured by dye to prevent confusion with lower octane grades, and it cost approximately 5 times as much to produce as standard 100 to 130 octane fuel. Production capacity remained limited throughout 1943, as refineries modified their equipment to handle the specialised processes required. British testing of prototype 150-grade fuel began in earnest during October 1943, when Rolls-Royce subjected a Spitfire 9 to extensive trials at their Hucknall facility. The test aircraft used a Merlin 66 engine, cleared to run at 18 pounds per square inch boost pressure, with 100 to 130 octane fuel, producing 1,710 horsepower at 3,000 RPM. Rolls-Royce engineers cautiously increased boost pressure while monitoring cylinder temperatures and listening for any signs of detonation. At 21 pounds boost, the Merlin produced 1,850 horsepower without distress. At 25 pounds boost, power output reached 2,020 horsepower, a 310 horsepower increase, or 18% more power from the same engine simply by using better fuel. The Spitfire 9's maximum speed increased from 408 miles per hour to 422 miles per hour at its critical altitude. Our rate of climb improved by over 500 feet per minute. More significantly, the 150-grade fuel allowed sustained high-power operation without the engine failures that had plagued earlier attempts to overboost Merlin engines using 100/130 octane fuel. The implications for Mustang performance captured immediate attention when USAAF and Rolls-Royce engineers met at Derby on October 23, 1943, to discuss what 150-grade fuel could mean for the P-51B. The Mustang already represented the finest high-altitude escort fighter in service, but engineers calculated that 150-grade fuel would allow the Packard-built Merlin V1650-7 to operate at 75 inches of manifold absolute pressure instead of the standard 61 inches, increasing power output from 1,490 horsepower to approximately 1,720 horsepower at critical altitude. The performance predictions proved startling. Maximum speed at 21,000 feet would increase from 440 miles per hour to approximately 450 miles per hour, while the climb rate would improve by nearly 1,000 feet per minute. Perhaps most significantly for bomber escort missions, the Mustang could maintain higher cruising speeds at altitude without burning excessive fuel, effectively extending its already impressive combat radius. The engineers projected that a P-51B running 150-grade fuel could catch and destroy any German fighter then in service, including the new Focke-Wulf FW190D with its 2,100 horsepower BMW radial engine. General Dwight Eisenhower's intervention accelerated the 150-grade fuel program when he wrote to Army Chief of Staff George Marshall and Army Air Forces Commander Henry Arnold on February 11, 1944, explicitly requesting that the new fuel be available for Operation Overlord. Eisenhower understood that air superiority would prove crucial to the invasion's success, and that every advantage in fighter performance could save lives on the beaches. His letter emphasized using 150-grade fuel to the fullest possible extent in fighters supporting the invasion, transforming what had been a research program into an urgent operational priority. The petroleum industry responded with remarkable speed, accelerating production schedules and modifying refineries to increase 150-grade output. Testing at Wright Field beginning March 20, 1944, validated the performance predictions and revealed some unexpected challenges. A P-51 B-15, serial number 43-24777, underwent extensive flight trials using 44-1 fuel at the increased power settings. Test pilots reported that the Mustang achieved 447 miles per hour at 26,000 feet, exactly matching predictions, while the rate of climb increased to 3,950 feet per minute at sea level, compared to 3,200 feet per minute with standard fuel. But the testing also revealed a problem that would plague 150-grade fuel operations throughout its service life. The massive doses of tetraethyl lead required for 150-grade performance created deposits inside cylinders that fouled spark plugs within 20 to 30 hours of operation. The spark plugs designed for 100/130 octane fuel couldn't handle the lead compounds created by combustion of 150-grade, requiring more frequent replacement and careful monitoring. Mechanics learned to recognize the symptoms of plug fouling, rough running at idle, and hesitation during acceleration, and developed procedures for more frequent plug changes. The P-47 Thunderbolt and P-38 Lightning underwent similar testing, with results that demonstrated both the potential and limitations of 150-grade fuel. The P-47D's Pratt & Whitney R2800 radial engine achieved 2,535 horsepower at 65 inches manifold pressure using 150-grade fuel, compared to 2,300 horsepower at 56 inches with standard fuel. Maximum speed increased from 433 miles per hour to 446 miles per hour, while the climb rate improved dramatically. But the testing revealed a serious problem with extended climbs when using water injection, as cylinder temperatures exceeded safe limits and several test engines suffered from detonation damage. The P-38J Lightning benefited less from 150-grade fuel because its turbo-supercharged Allison engines already operated at high boost pressures, though test pilots reported improved acceleration and climb performance. The conclusion from Wright field testing was that 150-grade fuel would provide the greatest benefit to Merlin-powered fighters like the P-51, where the two-stage supercharger could take full advantage of the increased boost pressure allowable. The first operational use of 150-grade fuel in P-51 Mustangs came in May 1944, as 8th Air Force fighter groups received initial shipments. Pilots were briefed on the new power settings, cautioned about spark plug fouling, and told to monitor engine instruments carefully during the initial flights. The instructions specified 75 inches manifold absolute pressure and 3,000 RPM for war emergency power, settings that would have destroyed Merlin engines using 100/130 octane fuel. Lieutenant Colonel Donald Blakesley, commanding the 4th Fighter Group at Debden, flew one of the first operational missions using 150-grade fuel on May 28, 1944, escorting B-17s to Magdeburg. Blakesley reported that his Mustang felt transformed, accelerating harder and climbing faster than he'd experienced before. More importantly, when Messerschmitt Bf-109G fighters attempted to intercept the bombers at 28,000 feet, Blakesley's flight easily caught them, despite the 109s having a significant altitude advantage. The German fighters, still using 96-octane C3 fuel when they were lucky, and 87-octane B4 fuel more commonly, simply could not match the performance of Mustangs running 150-grade. The appearance of German V-1 flying bombs on June 13, 1944, created an urgent requirement for maximum fighter performance at low altitude. The V-1 pulse-jet-powered missile cruised at approximately 400 miles per hour at 2,000 to 3,000 feet altitude, making it faster than most Allied fighters at that height. Spitfire 9s, Hawker Tempests VS, and P-51s using 100/130 octane fuel struggled to catch V-1s, and many bombs reached their targets simply because fighters couldn't intercept them. The introduction of 150-grade fuel transformed the V-1 defense, allowing these fighters to achieve speeds exceeding 420 miles per hour at sea level. Royal Aircraft Establishment testing of a Mustang III using 150-grade fuel demonstrated 382 miles per hour at sea level, a 25 mile per hour increase over standard fuel performance. This additional speed meant the difference between intercepting V-1s and watching them fly past, and within weeks of 150-grade fuel becoming available, Allied fighters were destroying V-1s at a rate that forced Germany to launch them primarily at night, when interception was more difficult. The operational experience with 150-grade fuel proved overwhelmingly positive despite the maintenance challenges. Air Defence of Great Britain issued an emphatic summary on September 18, 1944, stating that fighter squadrons using 150-grade fuel had demonstrated conclusively superior performance against both V-1 flying bombs and German fighters. The report noted that pilots universally preferred the higher power settings possible with 150-grade, feeling more confident in their ability to catch any enemy aircraft. The Spitfire 9's maximum speed increased from 408 miles per hour to 422 miles per hour, the Tempest 5 from 432 miles per hour to 445 miles per hour, and the Mustang III from 441 miles per hour to 455 miles per hour at optimal altitudes. These increases sound modest, but in aerial combat, where closing speed determines whether a pilot can achieve firing position, 10 to 15 miles per hour often meant the difference between victory and escape. 8th Air Force Fighter Command issued a request in late May 1944, demanding immediate supplies of 150-grade fuel for all P-47, P-51 and P-38 units. The urgency reflected combat realities, as German fighters introduced the Messerschmitt Me-262 jet fighter and improved piston engine types that threatened Allied air superiority. While no piston engine fighter could match a Me-262's speed, Mustangs using 150 grade fuel proved fast enough to intercept Me-262s during their landing approach, when the jets were most vulnerable. Several Me-262 kills by 8th Air Force P-51 pilots resulted directly from the additional speed provided by 150 grade fuel, allowing the Mustangs to position themselves near known Me-262 bases and catch the jets as they slowed for landing. The logistics of supplying 150 grade fuel to forward deployed units presented enormous challenges. The fuel cost 5 times more than standard aviation gasoline and required special handling because tetraethyl lead is highly toxic. Tank trucks, storage tanks, and refueling equipment had to be thoroughly cleaned before introducing 150 grade fuel to prevent contamination. The purple colour helped prevent mixing with lower octane fuels, but mistakes still happened, sometimes with catastrophic results when engines expecting 150 grade performance ran on diluted fuel. The petroleum industry struggled to produce sufficient quantities throughout 1944, with refineries operating at maximum capacity to meet both civilian and military demand. Priority allocation systems determined which units received 150 grade fuel, with fighter groups facing the most severe opposition getting first priority. The decision to supply 2nd Tactical Air Force units on the continent with 150 grade fuel beginning in December 1944 required an immense logistical effort. The fuel had to be shipped from British refineries to continental ports, then distributed through a supply network still recovering from the destruction of French transportation infrastructure. Antwerp became the primary port for fuel shipments after its liberation in November 1944, with tankers beginning to arrive in January 1945. The introduction of 150 grade fuel to frontline squadrons proceeded gradually, as mechanics modified aircraft engine cooling systems and trained pilots on the new power settings. By February 1945, most RAF fighter squadrons on the continent were operating with 150 grade fuel, giving them a decided performance advantage during the final campaigns into Germany. The performance improvements from 150 grade fuel extended beyond raw speed to encompass every aspect of fighter capability. Climb rates increased by 15 to 20%, allowing fighters to reach bomber formations faster and climb above enemy fighters for tactical advantage. Acceleration improved dramatically, particularly important during dogfighting, when pilots needed to build speed quickly after maneuvering. The ability to maintain high cruise speeds at altitude without burning excessive fuel extended combat radius, allowing Mustangs to escort bombers deeper into Germany while retaining sufficient fuel for combat. Perhaps most significantly, pilots reported feeling more confident, knowing their aircraft possessed a power reserve that could get them out of trouble when situations deteriorated. The metallurgical challenges of running engines at the power levels enabled by 150 grade fuel required careful monitoring and more frequent overhauls. The Merlin engine's aluminium alloy pistons, designed for 1,500 horsepower maximum output, were subjected to 1,720 horsepower with 150 grade fuel, increasing thermal and mechanical stress. Engineers reduced time between overhauls from 250 hours to 200 hours for engines regularly run at war emergency power on 150 grade fuel, accepting the additional maintenance burden as worthwhile for the performance gain. Connecting rods, crankshafts, and bearings all experienced increased stress, and mechanics learned to watch for early signs of fatigue that might lead to catastrophic failure. The German response to Allied use of 150 grade fuel remained limited by their inability to produce similar fuels in meaningful quantities. Luftwaffe engineers understood that higher octane fuels would allow their engines to achieve greater power, but the synthetic fuel plants producing most German aviation gasoline from coal couldn't easily create high-octane products. The additives required for 150 grade equivalent fuel depended on importing tetraethyl lead from neutral countries, and Allied blockades made such imports nearly impossible. German fighters continued using predominantly 87-octane B4 fuel, supplemented by limited quantities of 96-octane C3, giving Allied fighters using 150 grade fuel a performance advantage that German pilots found impossible to counter. Luftwaffe combat reports from late 1944 frequently mention Allied fighters, particularly Mustangs, that seemed impossibly fast and could not be caught or escaped from in level flight. The ultimate expression of what 150-grade fuel made possible came with the P-51 Mustang, a lightweight variant designed specifically to take advantage of high-octane fuel. North American aviation engineers reduced the P-51H's empty weight by 600 pounds compared to the P-51D through careful redesign of every component. The lighter airframe combined with the Merlin V1650-9 engine running on 150-grade fuel achieved a maximum speed of 487 miles per hour at 25,000 feet, making it the fastest American piston engine fighter to see production. The P-51H could outclimb, out-accelerate, and outrun any German or Japanese piston engine fighter, representing the pinnacle of World War II fighter design. Though the war ended before the P-51H could see extensive combat, the aircraft demonstrated conclusively that 150-grade fuel had transformed what piston engine fighters could achieve. The development and operational use of 150-grade aviation fuel represents one of World War II's crucial technological advantages, as significant as radar or cryptography in its impact on Allied victory. The ability to extract additional power from existing engine designs without complete redesign saved years of development time and billions of dollars in new aircraft production. The petroleum industry's capacity to produce high-octane fuels in vast quantities represented an industrial advantage that Axis powers could not match, demonstrating how America's economic strength contributed as much to victory as its military forces. The chemists, engineers, and refinery workers who developed and produced 150-grade fuel rarely received recognition for their contributions, but their work gave Allied pilots the performance margin that often meant the difference between survival and death. The lessons learned from 150-grade fuel development influenced post-war aviation. The understanding that fuel chemistry could dramatically affect engine performance led to continued research into higher-octane fuels and alternative additives as environmental concerns about lead grew. The jet age would eventually make octane ratings irrelevant for military aircraft, but the fundamental insight that fuel quality matters as much as engine design remained valid. Modern racing fuels and specialized aviation fuels still use advanced additive packages to maximize engine performance, a direct descendant of the work done developing 150-grade fuel. Veterans of the 8th Air Force and RAF fighter squadrons who flew on 150-grade fuel remembered the distinctive purple color in their fuel tanks and the extra power available when they pushed throttles forward to war emergency settings. They recalled the confidence that came from knowing their Mustangs could catch anything the Luftwaffe flew, that they could accelerate away from danger when outnumbered, that they possessed a technological edge that Germany could not counter. These men understood that the chemists who never saw combat had given them a gift measured in additional horsepower and extra miles per hour, advantages that saved lives and shortened the war. The story of 150-grade fuel is ultimately about how wars are won, not just through courage and tactics, but through the unglamorous work of scientists and engineers solving technical problems. The petroleum chemists optimizing additive packages, the metallurgists strengthening engine components, the refinery workers producing fuel under wartime pressure, all contributed to a technological revolution that transformed Allied fighters into the fastest, most capable piston engine aircraft ever built. When Captain John Peterson caught that V-1 flying bomb over the English Channel in June 1944, when Lieutenant Colonel Blakesley's Mustang ran down a fleeing Messerschmitt, when P-51H pilots achieved speeds approaching 490 miles per hour, they were experiencing the direct result of chemical engineering as much as aeronautical design. The purple fuel in their tanks represented the accumulated knowledge of petroleum chemistry applied to the desperate needs of war, proving that sometimes the difference between victory and defeat comes not from factories building new weapons, but from laboratories making old weapons work better.